Okay, let's do some quick calculations involving magnetic induction. So what we know is that Faraday's law tells us that the induced EMF is proportional to the rate of change in magnetic flux, where magnetic flux is given by the field times the area of the loop times the cosine of the angle between the normal to the loop and the magnetic field lines. So we don't measure the angle from the surface of the loop, we measure it from the normal to the loop. The n there is the number of turns in the loop, and the minus sign tells us that the voltage induced is such that it opposes the change in flux. If we move a wire in a magnetic field, if it's perpendicular to the magnetic field, the induced EMF is BLV, where B is the field, L is the length of the wire, and V is the speed at which the wire is moving. So let's do a couple of examples. So first of all, let's calculate using our two equations the induced EMF in a circular loop that's got a 12 centimeter diameter. So the diameter is 12 centimeters or 0.12 meters. The radius then is going to be half the diameter, so 0.06 meters. And the area of the loop is pi r squared. It's going to be pi times 0.06 squared, which is a small number, 0.0113 meters squared. Okay. And the magnetic field changes from plus 0.52 Tesla to negative 0.45 Tesla. So B initial is 0.52 Tesla, B final is negative 0.45 Tesla, and it changes in 180 milliseconds, so delta T is 180 milliseconds or 0.180 seconds. Okay, so I know B, I know A. I need to figure out what is theta. Well, they tell me the field is perpendicular to the loop. So if again, let me go up in the top right corner. If I draw the perpendicular to my loop, the magnetic field is also perpendicular to the loop. So the magnetic field is parallel to the normal. So theta is equal to 0. So I know all my numbers. Now it's just a matter of plugging them in. So EMF, how many turns do I have? Well, it doesn't mention anything about turns in the problem, so if that's the case, I assume I have one turn. So my EMF is equal to minus the change in flux over the change in time, so it's going to be minus phi final minus phi initial over my 180 milliseconds or 0.18 seconds. So I need to know phi final and phi initial. So the final flux is equal to B final times the final area, which is always the same, times the cosine of 0. So that's going to be negative 0.45 Tesla times the area, 0.0113 meters squared. Cosine of 0 is just 1. So I get a final flux of negative 5.085 times 10 to the minus 3 Tesla meters squared, and we also have the unit of Webers for that. Initial flux is going to be B initial A cosine theta. If you had a problem where B stayed the same and the area changed, then you would do A final and A initial. If you had an angle where if you have a problem with the angle changes, you do theta final and theta initial. All right, so put in our numbers. The flux is 0.52 Tesla. Area is still 0.0113 meters squared. Cosine of 0. I get plus 5.88 times 10 to the minus 3 Webers. So the change in flux then is going to be final minus initial, minus 5.085 times 10 to the minus 3, minus positive 5.88 times 10 to the minus 3, divided by delta T, which is 0.180. And if I put that in, I get a voltage change of positive 0.061 volts. Okay, so the final answer is 0.061 volts. Okay, let's do a problem where we have a moving rod. So for a moving rod, E equals BLV. And this problem, they say we have an EMF of 120 millivolts. So that's 0.12 volts. Moving in a 0.9 Tesla field, so B is 0.90 Tesla. If it's 13.2 centimeters long, so that's L is 13.2 centimeters. I need to put that into meters, so 0.132 meters. And what's its speed? Okay, so it gave me 3 of the 4 things in the equation and asked me to find the 4th. So V is equal to E over BL. So just plug and chug. 0.12. B is 0.90. L is 0.132. And so I get that the speed at which it's moving is 1.01. And let's see, I need to round that to 1.0 units for speed, meters per second. Okay, so that's pretty straightforward. All right, so let's move on and talk about the primary reason why we use magnetic induction. Keeps us all alive. So all power except for that generated by solar panels is generated by rotating a loop inside a magnetic field. So if you look at a wind turbine, the wind turbine is spinning on an axle that causes a loop to rotate inside a magnetic field. As it rotates in the magnetic field, its angle to the field changes, and so that induces a voltage, and that's what we use for powering everything in our lives. Okay, so the EMF that's generated is the number of turns in the loop times the field times the area of the loop, and then omega is the number of times, the angular frequency, the number of times it spins around per second. In this country, we use a frequency of 60 hertz for the power that's generated, and so omega is going to be 2 pi times 60. And of course, because the loop is rotating constantly, the EMF is changing all the time because the angle's changing, and what we see is a sine function like you see below, where the voltage goes up and down like a sine wave with a maximum magnitude that's equal to the numbers in front of that sine function, NB omega times A. Okay, so if you have a hydro plant, the water coming over the top of the dam spins a water wheel that turns a loop in a magnetic field. If you have a gas or coal or nuclear power plant, what they do is they use heat to boil water. The steam rises and it pushes on a wheel that rotates a loop inside a magnetic field. So magnetic induction is extremely important to everyday life because we use it to generate our electricity. If your power goes out in a storm and you have a generator at home, what that generator is doing is it's using a gas engine to rotate a loop in a magnetic field and create electricity. All right, so another side effect is that if we have something that's plugged into the electricity and the electricity is changing all the time, if there's a piece of metal nearby, that current that's changing all the time is going to create a changing magnetic field inside the piece of metal, and that changing magnetic field is going to cause little loops of current to flow inside that piece of metal. We call those eddy currents because they're like eddies or whirlpools in the current of a river. And those things can turn mechanical energy into heat. And if you drop a conductor into a magnetic field, it's going to cause that conductor to slow down because it's going to turn the kinetic energy into heat energy. So an example of this is that if you take your charger for your phone and you plug your phone in to charge it up, you know that when you pull it out of the wall, it's slightly warm. The reason why it's slightly warm is because it consists of a metal core with coils of wire wrapped around it. The wire carries current from the wall that's changing all the time, and that induces eddy currents inside the piece of metal inside your charger. And so when you pick up your charger and it's warm, you know it's had current flowing through it recently. And so you can also tell if your phone's been charged for quite some time. If you pull your charger out and your charger's cool, then you know it hasn't had any current flowing through it. Okay, so that moves us on to talk about what is that charger actually doing. Well, what that charger is doing is it's taking the power from the wall, which is at 120 volts, and it's turning it into, usually for like an iPhone charger, those are usually about 5 volts. So it's taking the 120 volts from the wall and it's turning it into a lower voltage that's safe for charging your phone. So what a transformer is it's an iron core, usually, because the iron is good for conducting magnetic fields. And you wrap 2 coils of wire around it. One of the coils of wire comes from the primary side that you plug into the wall, and the other coil of wire goes to the secondary side, which goes to the charger that connects to your phone. And by varying the number of turns on the primary and the secondary side, we can vary what voltage we get on the secondary side compared to the primary side. What happens in the transformer is that when you have a changing current inside the primary side that's hooked up to the wall, it creates a changing magnetic field that goes around this iron core. So that's going to cause a changing magnetic flux inside the secondary side. So every time the primary voltage goes up and down, the secondary magnetic field is going to go up and down. That's going to create a voltage on the secondary side. And the voltage on the secondary side is going to depend on the voltage on the primary side, and it's going to depend on the ratio of the turns in each coil. So it's directly, the voltage on the secondary side is directly proportional to the number of turns on the secondary side. And so you can make a transformer that will either take the voltage from low to high, in which case we call it a step-up transformer if the secondary is higher than the primary, or it can go from high to low like your phone charger, and that's called a step-down transformer. If we assume that energy is conserved, so the power on the secondary side is equal to the power on the primary side, which is almost true. We lose a little bit of that power to heating inside the core. Then the ratio of turns on the secondary to the primary is inversely proportional to the ratio of turns. So you see that in this case the fraction is the other way up than what we had for the voltages. Okay, so what do we use it for? Well, the primary reason that transformers were invented was to allow us to conduct electricity from a power plant that's a long way away from where our house is without losing a lot of power. So when power goes down the line, we lose energy at the rate of the current squared times the resistance, and we know the longer the wire, the higher the resistance. So if we have a wire that's 100 miles long, it's got quite a high resistance overall. So to minimize the power loss over a long distance, we want to have the current as low as possible, which means that, remember, power is I times V. If we want the current to be low, the voltage has to go up. So what happens is that the power plant, we have step-up transformers that take the voltage from something around, say, 12,000 volts that's generated at the power plant up to about 250,000 volts and very low current that goes through those high transmission towers that march across the landscape. Then when it comes into town, okay, so where was I? All right, so when the power comes back into town, it goes into a step-down transformer that takes it from the 500,000 volts back down to about 2,400 volts to go along the streets. That's what you see going along on the power poles. And then when it gets into your neighborhood, it goes down through a step-down transformer, which are those little gray cylinders that you see on the power poles, or if you have in-ground electricity, it's sort of the green boxes that are on the ground. Those step it down to the 240 volts that goes into your house. Remember, if you had DC power, the power would always be constant, and so we would not be able to use a transformer because there would be no change in flux to create any voltage on the secondary side. So the transformers only work with alternating current power supplies. So let's do a quick calculation. So here we have a toy train. It has 3 volts on the secondary side, and we want to know if you plug it into the 120 volts household voltage, what should the ratio of turns on the primary to the secondary side be? So we know VP is 120 volts. The voltage on the secondary side, that's on your train, so that's 3 volts. And they're asking us to find NP over NS, the ratio of turns on the primary to the secondary. So we know for voltages, the ratios are the same way up. So NP over NS is VP over VS. And that's simple. I just put in my numbers, 120 over 3, which is 40. Okay, so the number of turns on the primary to the secondary, the ratio is 40 turns. So there's 40 times more turns on the primary side than the secondary side. Okay, so what I want you to do is an example of each type of calculation. So I want you to calculate the change in flux through a loop to calculate the EMF that's induced. And this time what we're going to do is we're going to change the angle of the coil to the field. So remember, you need to know the angle between the normal to the loop and the magnetic field. So you need to read the problem carefully. And the second one, we want to calculate the voltage and current on the primary side of a transformer given the voltage and current on the secondary side and the number of turns on the primary and secondary sides of the coil.